Hello everyone, in this video we are going to solve the problem related to the state space representation of the electrical system. Okay, so for the state space representation of the electrical system we have two equations. One is state equation and another is output equation. So what is the output equation? So the one equation is x dot equals to ax plus bu, which is called state equation, and y equals to cx plus du, which is called output equation. Okay, so here x dot represents the state variables, where x dot equals to x1 x2, x dot equals to x1 dot x2 x3. We can suppose them as state variables. Okay, state variables. Similarly, here x dot gives the state equation and y gives the output equation. Okay, so in order to represent the given electrical system in the form of state space representation, okay, so we first identify the state variables. State, what is the meaning of variable? At first we must be clear in the state variable. Okay, so variable is something that varies, isn't it? Variable is something that varies. So um, in the figure we can see that we have resistor, inductor and capacitor, but on passing the current through the resistor, the resistance does not vary. Okay, on changing the current, the value of the resistor does not vary, but on changing the value of the current, the voltage across the inductor and the capacitors, voltage across the inductor also varies, and also the voltage across the capacitor also get varies. So how many variables are there? There are two variables. Okay, there are two state variables. This is what it is said in this first step. There will be two state variables because the inductor and the capacitor get varies. Okay, one is current through inductor and another is voltage across the capacitor. That is, if the current passes through the inductor and the voltage passing through the capacitor make them varies. So in all the problems of the state space representation, we always apply Kirchhoff's voltage law and Kirchhoff's current law, KVL and KCL. Okay, so here we have, now at first let us apply the KVL law. Okay, so here we have input voltage V in equals to, we can write input. What does the KVL say? Input voltage equals to sum of incoming voltage equals to sum of outgoing voltage. So we can write B in equals to IR plus voltage across the inductor is L di upon dt, plus BC means the voltage across the capacitor, which is also called output. Okay, so we are changing its form, that is, we are dividing the both side by L, isn't it? So we get the VIN upon L minus IR upon L minus BC upon L, and we got the form di upon dt. Why we are getting di upon dt, or why we are calculating di upon dt? Because we need the state equation. So state equation is given by x dot. X dot means derivative of something. Okay, so here di upon dt represents I dot, isn't it, which is the form of the state equation. So we are converting this form into the derivative. Okay, so we got di upon dt equals to minus r by l I minus 1 by l bc plus 1 by l b in. Okay, now similarly applying KCL, Kirchhoff's current law, we got that I equals to C dBc upon dt. Okay, so the current flowing through the capacitor can be expressed as I equals to C dBc upon dt. So for state equation, what we have to calculate? We have to calculate the derivative of BC, isn't it? For state equation we need derivative. So how can we find out the derivative? How can we keep the equation in the derivative form? Just by arranging the equation, the following equation: I equals to C dBc upon dt. So here we got dBc upon dt equals to 1 upon C times I. Okay, now we have to represent, we got the, in the both case, in the both case we got the derivative of the current and voltage. So now we can write the state equation. One question is that why we are calculating the derivative of the current and voltage? Because uh, as in the here it is said that there will be, as we have already studied, that there are here we can see that there are two state variables. So one is current through inductor and another is voltage across capacitor. That is, we have already stated that the IL and BC are the state variable. So we need the derivative of IL and BC. So we are calculating the di upon dt and dvc upon dt. Now arranging them in the matrix form, what we get is di upon dt equals to, okay, arranging these two equation. Okay, we have to arrange these two equation in the matrix form. So we have di upon dt and another is dvc upon dt. How this equation is arranged? This equation is arranged in the form of x dot equals to ax plus bu. So what are the x dot? X dot, what does x dot represents? Di upon dt and dvc upon dt equals to ax. Let us suppose our x be I and bc. Okay, I and bc. Here u represents input. Okay, u represents input vector. U represents input vector and x represents the state variables. So what are the state variables? That what we suppose the derivative, isn't it? Here we have state variables are IL and BC. So x means IL and BC, or we can write IL as I. So x, here x is I and BC, and what are the coefficient of I and BC? In the first equation the coefficient of I is minus R by L, and in the second equation coefficient of I is 1 by C. Similarly, in the first equation coefficient of the BC is minus 1 by L, yeah, and in the second equation the coefficient of BC, we do not have any coefficient of BC, so the coefficient of BC is 0. Similarly, plus, okay, we need the input vector. Do we have input vector? S, we have input as B in. So but we do not have B in both equation. Okay, so we are writing U as B in, and what is the coefficient of B in first equation? 1 by L, but we do not have any coefficient of B in second equation, so we write it as 0. Now, which is in the form of x dot equals to ax plus bu, which gives the state equation, isn't it? As we have already said that it gives the state equation. Okay, now we need another is need output equation also. So output equation is represented by y equals to cx plus du. As we have already seen in the figure that the output is given by the voltage across the capacitor, isn't it? So considering voltage B out as BC, okay, we can write that considering B out as BC, we have B out equals to, in the both equation in the both equation in the both equation x represent the same things, okay, which means state variables. So what are the state variables in the equation? I and BC. So do we have in the output is given by the BC. So in this BC, as we have said there, the BC gives the output voltage, isn't it? So we have considered the output voltage as BC. So we can write that BC. Do we have the coefficient of what are our output? Does the inductor current is giving us any kind of output? No. So we do not have, our state variables x remains the same, but we do not have the coefficient of I in the, or we can say that we do not have, the current does not give any type of output, only the BC is giving output. So we can write there the coefficient of I as 0 and the coefficient of BC as 1, which is in the form of y equals to cx plus du. We can, we do not need to write du also, because we do not have any kind of du in the output. Okay, so we do not have to mention it in the matrix form. So in this way we can solve the state space representation of the electrical system. Thank you.